Alright, so we have these equations. Okay, we've been working on how to solve things. We did the whole grid, and this example dealt with no acceleration. Alright, so nothing was speeding up or slowing down, we just had a constant velocity. Okay, so some of these you guys are going to do on your own. So this one's homework right here. We did this one in class. Alright, and that one we were solving for an acceleration. Just using our acceleration equation right here. Example number 4. This one's homework. 5 is homework. And 6 we will do in class. Alright, so let's do this one together. You are designing an airport for small planes. One kind of airplane that might be used at this airfield must reach a speed before takeoff of at least 27.8, and then they give us the acceleration. Okay, if the runway is 150 meters long, can this plane reach proper speed for takeoff? So we have our things that we need to do. All of these are velocity graphs. Okay, on each problem, I want you guys to draw the velocity time graph. So for this one, let's try that. List your known data and draw your graph, and then we'll go over it. Okay, so what are some things we know here? Okay, we got acceleration, so let's put that down. Acceleration is 2 meters per second squared. Alright, what else? To be final, planes are going to get up to 27.8. That's right. They have to start from rest, right? They're taking off. So it doesn't say it in the problem, but we're going to put down that VI equals 0. Okay, and then there's this data. We've got a runway of 150 meters long. We are kind of testing out that number. We don't know if that number actually works. So we're going to put delta x equals 150. And I'm just going to put some question marks after it. Okay, we're talking 150 meters. So we can't really use that number because we don't know if that number is valid. Alright, there's actually 2 ways to do this problem. Okay, our graph. Starting from rest, and we're going up to some speed at constant acceleration. Needs to look something like that. So we know that the slope equals 2. And we could label the axes and all that. We don't know the time though. We don't know how long this thing's going to be accelerating for. Okay, and then over here, equations and solutions. Alright, since we don't know time, let's check this out. here's what we want to do. We want to solve for the runway length. We want to solve for delta x and compare it to this number. Things that we know. We know v final, we know v initial, and we know the acceleration. Alright? So what I want you guys to do, make sure you rearrange this first and then plug your numbers in. Alright, so if I want to get delta x by itself, do I deal with the vi squared first or the 2a? I have to move the vi squared to the other side and then divide. Alright, we have to do our steps in the right order. So I'm going to say vf squared minus vi squared equals 2a delta x. And now I can divide the a delta x to the other side. Alright, what I'm going to end up with is this. Alright, now we just have to plug in numbers. Alright, so punch that in, what do we get? Alright, sounds good. Okay, oops. It's not a speed. Okay, so we get 193 meters. And if we wanted to be really picky about sig figs, oh no, that's 3 sig figs, we're good. Okay, so will the 150 work? Not enough runway space, okay? Those planes are going to crash. Alright, it's got to be a minimum of 193. So this right here is the answer to part B. Needs 193 meters to take off. Okay, any questions on that one? Alright, we're going to do one more and that's it for the day. How much time do we have? 13 minutes, perfect. Okay, let's turn to example number 8. Okay, so these two are homework. 9 and 10. Yeah, 7. So you guys have 5 to do at home. Alright, we did 5 in class, 5 at home. The UT is not due until Friday. Okay? Well, doing these and going over these will help you with the UT.
So technically we know everything.
Technically you know everything to do the UT, but these will kind of help solidify it. Yeah. Alright, number 9. Or sorry, 8. Okay. Estimate the stopping distance for a car. Calculate the total stopping distance for an initial velocity of 100. Notice the units. And assume the acceleration of the car is negative 6 meters per second. And we need to add a squared right there. And then it gives us some interesting data. The average reaction time is half a second. Okay, what's that mean? Reaction time.
That'll be starting at 45.
Okay. It's gonna, well, we're gonna start at this speed. For the time, okay. let's go over here. This is a little bit more complicated problem. I would like you guys to do a diagram for situations like this. So we're going to have this initial distance here where the person hasn't even hit the brakes yet. All right, that's the reaction time. Okay, then there's going to be this distance here where they are braking. So I'm going to put stopping time. All right, now we've gone over how to convert, so I'm not going to take the time to, what's that come out to be? I'll just tell you. Did anybody convert it already? Yeah, 27.7. Okay, so this in meters per second, 27.7. Okay, so on our diagram, they are starting at 27.7. After the half second, still going 27.7 because they have not hit the brakes yet. And let's put 0.5 seconds right here. Okay, then some time's going to go by that we don't know. We know the acceleration here is -6. And we know one other piece of info. What is that? Yeah, V final equals 0. Okay, and we could say that this is equal to our V initial. Okay, now our known data, didn't we kind of just list that over here on our diagram? Do we really need to list it again? Not really. Okay, let's put over here that delta x is what we were trying to find. And we're going to have to find two different delta x values. We need this one and this one. To help us out with that, before we start doing a bunch of equations, let's do the VT graph. What's that going to look like? Okay. Alright, well, let's look at the speeds. Okay, we got this one, then 0. So for a little while, we're going to go constant speed. That's for half a second. And then we're going to have a constant negative acceleration. Okay, so -6 equals slope. Okay, notice 0 equals our slope right there. What else do we know about this VT graph? There's only 3 things we can do with the graph. Okay, yeah, the area. Okay, good. The area will give us the delta x. Now we have 2 areas to calculate. Okay, we have A1 and A2. And if we add them both, then we'll get the total stopping distance. So for our equations and solutions part, okay, let's do A1 right here. Okay, since there's no acceleration, our delta x is just our velocity times our time. And we could put a bar over that saying average velocity if we wanted to. And that's on your page of notes on the front side. So our velocity is 27.7. And the time is half a second. Okay, so let's figure that out. get 13.85. So before the person's even hit the brakes, they've noticed something ran out into the road. All right, they've already gone 13.85 meters at this speed before they've even started to stop. Physics should make you a better driver, right? Hopefully. Okay. All right, now A2. A2, we have an acceleration happening. Look at your three equations. Which one do we want to use here to get the distance? Okay, do we know time? No, we don't know time. Okay, so we can't use that one. All right. This one, do we need to know time? No, so we have all of the info to use this one. Okay, now before we do that, check this out. You could use this to find time, right? Because we know these three things. And then we could go and use this to find delta x. Okay, so two ways to do it. I always choose the way that's simplest. So let's do this. Okay, and we need to rearrange it for delta x. So we did that on the other page. First step's going to be to subtract it over, and then we'll have a final product that looks like this. Okay, all right, what do we get? I rounded up to 28 when I did this, so I'm going to punch it in again. Okay, I got 63.9. Alright, then we got to add on our 13.85, and we'll get the total distance of 77.8. Okay, and we could round that to 2 sig figs if we want and say 78 meters. Alright, so two-part problem there. We had to do two different situations because the acceleration was changing there from 0 to -6. Okay? Alright, so finish the rest of those on your